Good morning, everybody. So, today we are going to talk about fast reactions, techniques for studying fast reactions. So, let us see again the outline that we have talked about reaction rates, rate laws, effect of temperature on reaction rate, complex reactions, theories of reaction rate, kinetics of some specific reactions, kinetics of catalyzed reactions. So, now today we will talk about fast reactions. Now, as we all know that chemical kinetics affects everyday life, determines how fast insects walk, how quickly plants and animals grow, even how fast their hair grows. I mean how fast hair grows on your head, that is also a part of your this chemical kinetics. Very important in chemical process, that is selectivity and activity of chemical reactions determines how well chemical processes work. Anyway, so reactions can be very slow reaction, it can be moderately fast, or it may be very fast. Okay. So, slow reactions are easy to follow, that is maybe with time you can follow the concentration of some reactant or maybe some product. Okay. Suppose one reactant is depleted, so you can find out the concentration if it is depleted slowly. Okay, but if it is depleted slowly, then suppose taking first reading, and whenever you are ready to take the second reading, by that time gap, if it is completely depleted, or maybe even before the start of your measurement, if all the reactants are depleted, all the reactants are consumed, then it is difficult. It is by conventional method you cannot find out you cannot follow the chemical reaction. Okay, in terms of kinetics, you cannot follow the kinetics. So, there are a wide range of techniques available to study fast kinetics. That is, the thing is that the reaction happens in a very short period of time. In conventional titrometric method, suppose consider the reaction of ester, that is hydrolysis of ester by acids or maybe by alkali. So, what you do? You take some ester in a conical flask, say it methyl acetate or maybe ethyl acetate, you take in a conical flask. Then what you do? You add your that is reagent, your acid or base, that may be your catalyst, or maybe in other way you can take your acid or base in your conical flask and then half discharge, note down the half discharge of your ester. Okay, and then what you do after it is mixed thoroughly, that is the moment the half discharge time is noted, that is your 0 time. So, then you swirl the reaction mixture so that your reactants, that is acid or alkali, and your ester is mixed thoroughly, and then maybe you wait say for 4 to 5 minutes, take out some definite amount of aliquot, maybe 5 ml, and then you discharge that 5 ml aliquot into a ice cold water to arrest the reaction, and then you titrate with it is basically an acid base titration with an appropriate indicator. But the thing is that between 0 and 5 minutes, if all the reactants are depleted, that is if most say 90% of the reactant concentration is depleted, then what will you do? You will be getting only 1 point, 1 point on your graph paper. So, that is not sufficient to follow the kinetics. So, that is a real problem if your reaction is very fast. Okay. So, in a moment everything is completed, all the reaction is completed. So, it is difficult using the very conventional method to follow the chemical kinetics of the first reaction. So, in this case, you know, a number of techniques are available, like flow techniques. These are typically used to study reactions occurring on time scales of seconds to milliseconds. Milliseconds means 10 to the power minus 3 second. Okay. So, that is 10 to the power minus 3 means 1 by 10 to the power 3 second, that is 1000 part. Okay. 1 part, that is, if you divide your 1 second into 1000 parts, then maybe 1 part will be your 1 millisecond. Okay. So, in the simplest flow method, reactants are mixed at one end of flow tube, here one end of flow tube, and the composition of the reaction mixture is monitored at one or more positions. That is, here, you know, the reaction mixture is flown this way. So, here you can monitor the composition of your mixture by a movable detector. Okay. So, that is monitored, that is, composition of the reaction mixture is monitored at one or more positions along the tube by any suitable, you know, detection method. Okay. So, you mix over here, say this is your reactant 1, this is your reactant 2, this is an injection method. So, you inject into this reaction vessel, okay, and then you allow, you continuously, you know, add your, you know, continuously inject your reaction, I mean reactants into this chamber, and it is allowed, I mean the reaction mixture is allowed to flow through this tube, and you detect by a suitable method the composition of the reaction mixture. Now, if the flow velocity along the tube is known, measurements at a different position provides the information on the concentration at different times after the initiation of the reaction. Okay. So, the moment you mix, this is your initiation of the reaction, and then it is, you know, it is flowing through. Okay. So, flowing through this tube, and then you measure. So, that means if this flow rate is known, then you should be able to find out the time dependent concentration, okay, along this tube. That is the time dependent concentration of certain reactant or maybe certain product. Okay. So, this is one way. So, in this case your detector is movable. In other case, the injector can be movable, that is, your detector is fixed and the injector can be movable. It may be moved from maybe this position to this position. Okay. So, in the second method, this detector may be in a fixed position, but moving injector can be used to inject one or more reactants into flow tube at different positions relative to the detector to study the time dependence of the reaction composition. So, there could be, I mean, you can have two ways. In one case your detector is movable, and in the other case your one of the injectors or maybe both can be moved. Okay. So, this way you can, you know, you can find out the time dependent concentration. So, that is the goal of, you know, studying, I mean, to know the kinetics, you should know the time dependent concentration of certain reactant or maybe product. Okay. So, it is a continuous flow method I just talked about. So, continuous flow methods have the disadvantage that relatively large quantities of reactants are needed. Okay. And very high flow velocities are required in order to study fast reactions. For fast reactions, since it is occurring very fast, so to compete with that speed, you should pass your reaction mixture very fast through your flow tube. Okay. So, that is a difficulty, you know, that is a difficulty. So, that is why, you know, another modified version of this flow method has been devised. So, it is called another method which is called the stopped flow method. In this method, a fixed volume of reactants are rapidly injected into a reaction chamber, and it is mixed by a syringe fitted with at end stop. Okay. So, what is happening that here it is fitted, this syringe is fitted, it is movable maybe. So, it is stopped, flow has been stopped at this point, and now what is happening, you are injecting. So, slowly it is going out, this syringe is going out. So, you are injecting, that is injecting this way, and this syringe is going out. So, your injectors here and here, these two are pushed in and it is pushed out. Okay. So, the composition of the reaction mixture is monitored here by the help of a detector spectroscopically as a function of time after mixing at a fixed position in the chamber, that is maybe here at a fixed position. This can be designed to allow measurement on very small sample volumes, making the stopped flow method very useful for studying the biochemical kinetics, as for example enzyme kinetics or enzyme reactions. So, in previous method, I mean flow method, it is continuously flown out the mixture, but here you see that there is a syringe which is stopping the flow, and slowly it is coming out as your reactant syringes are pushed in. Okay, so, it is a modified version, and and it requires lesser volume of your reactant. So, it is now widely used to study biochemical kinetics, the reactions which are occurring very fast. Okay, very fast reactions can be followed. Not only biochemical reactions, maybe other reactions as well can be studied with using this stopped flow method. Okay. So, so these two methods are dependent on the, I mean is based on the flow technique. Next is another method which I will discuss maybe in a later part of our talk, maybe in the next talk in details, but here we are I am just trying to give you the idea of another technique for studying the fast reactions. It is flash photolysis. I guess all of you have seen flash of light whenever you use a camera, okay, to shoot, I mean some photograph. Okay. So, the moment you click, it flashes, depending on whether you are using flash or not. Maybe not in daytime, but maybe when the daylight is less, or maybe in the night time, you have to use a flash, otherwise your objects are not visible. That is why you have to have you generate some light source. I mean you use some light so that your objects are visible. It is an artificial way of lighting your objects. So, you click, flashes. Okay. So, that's called a flash. Now, this flash can initiate a chemical reaction. Okay. Maybe some photochemical reaction can be initiated with this. The reactions which are very much dependent on the amount of photon that is falling on the reaction mixture. Okay. So, flash. So, this flash is used, and depending on the duration of the flash, if it is very fast, that is clicks and then it goes maybe, or maybe sometime it remains say for some period of time, maybe several milliseconds, it can stay. Okay. So, depending on the stay time of this flash, whether it is long flash or it is a short flash, you can study different reactions, I mean reactions of different fastness or maybe differing in slowness. Okay. So, reaction, in this case the reaction is initiated by a pulse of light. It's called a flash, like your flash of your used in photography. Okay. So, that dissociates a suitable precursor molecule in the reaction mixture, producing reactive species for initiating the reaction. The concentration of the reactive species is monitored as a function of time spectroscopically, okay, because spectroscopic methods are detectors used in spectroscopic methods can be fast. Okay, they can detect, I mean these detectors can detect your signal very fast, that is its time resolution is high compared to other things. So, optical detectors are very useful in this case. So, that is why spectroscopic detection methods are used here. Okay. So, maybe it is by using absorption spectroscopy, that is absorbance as a function of time, or maybe fluorescence spectroscopy, that is in that case we monitor the fluorescence intensity as a function of time. So, fluorescence is basically getting up some photons out of some process, maybe it is a physical process or maybe it is a chemical process. Chemical process may be a chemiluminescence, physical process is simply phosphorescence or fluorescence. So, net thing is that you are getting some photons and you are just measuring the photon intensity, I mean number of photons crossing per unit area. Okay. So, you are measuring intensity as a function of time. Okay. So, with the help of a photo detector, maybe photomultiplier tube, maybe photodiode. So, these two use the simple concept of photoelectric effect, okay, that when photons are falling on some surface, additional I mean secondary electrons are generated. So, that electrons are detected and a current is induced in the circuit. So, that is related to the, I mean that is corroborated with related to your amount of fluorescence that you are getting. So, there is a one-to-one correspondence, okay, between amount of photons generated, okay, and the current you are getting in this in the electrical circuit. Okay. So, maybe spectroscopically or I mean absorption spectroscopy or maybe fluorescence technique, the shortest time scale in which the reaction can be studied using this technique, okay, is determined by the duration of the flash or time width of the pulse. Okay. So, the thing is that in earlier days when manual photography has been used, in that case what is happening that if your flash is not synchronized with your shutter, then maybe your photograph could look like that it is half illuminated and half dark, because of the fact that the time for which this shutter was open, okay, is much it is happening that this shutter is doing like this, it is moving and then coming back. So, maybe the time for which the shutter was half open, during that time maybe the flash was on, and the remaining portion when the shutter was just closing, that time the shutter, I mean the light was off. So, what has happened is that during half shutter the light was on, means half portion of your photograph is illuminated and half is not illuminated. So, that is why your shutter speed and your flash duration is very important, that is synchronization is very important. Okay. So, that means it is the width of your flash that determines your ability to follow a particular reaction or not, okay, whether you will be able to follow a first reaction or you won't be able to follow the first reaction. Okay. So, that is why flash time is important. So, the flash, it is determined by the duration of the flash, or maybe full width half maximum, that is the time duration. If you plot the intensity as a function of time like this, say this is your intensity, your time. So, your flash could be like this, it could be like this, that is, it is on, then remaining steady for some time and then it is off, or maybe it can be like this. So, width means this is your full width half maximum. Okay. So, this width is basically determining your how fast you will be able to detect a reaction or not. So, that is width of your flash is very important. Now, earlier days flash is provided from the discharge lamp with duration in the region of tens of microseconds to several milliseconds. Okay. Like discharge lamp, like you see like in camera, similar to that. Okay. But in most modern experiments the flash is provided by a laser pulse. Okay. So, in our next lecture I will give you brief introduction of laser. So, laser is perhaps maybe many of you have seen, that is it is a laser pointer that is generally used in some demonstration, that is when somebody is talking. So, laser pointer is used to point out, I mean that is intense dot of light that is coming out of a pin like substance like this, and the laser light is coming out. Okay. Okay. So, you just point out where, I mean the portion you want, you can highlight, or maybe in some laser show you can, I mean you have seen perhaps laser light show. So, where lots of different types of patterns can be generated. So, this lasers can be pulsed, or maybe it can be continuous wave, I mean it stays for with time, or maybe it goes on and off like that. That's called a pulsed laser. So, typically duration of a pulsed laser could be nanosecond, 10 to the power minus 9 second, or it may be even less, I mean maybe femtosecond, okay, 10 to the power minus 15 second. So, this laser pulse is very important. So, if you want to study very fast reactions, then you may need to use femtosecond pulses, or maybe if it is moderately fast, you may need to use nanosecond pulses. But depending on the systems that you are using as the lasing substance, your wavelength will be generated. Okay. It may be in IR region, it may be in visible, it may be in UV region, depending on what type of material or what type of lasing system you are using. Anyway, so for studying fast reactions such as electron transfer reactions, maybe in photosynthesis, okay, laser pulses as short as few tenths of femtosecond, okay, 10 to the power minus 15 seconds are used. Okay. So, that is why, I mean you can choose using different duration, differing in duration of your pulse, you can choose your system. I mean whether it is a fast reaction, if it is a very fast reaction you use femtosecond pulses, if it is moderately fast then maybe accordingly you can choose your light, I mean pulse width. So, the flash photolysis has the advantage that because reactants are produced from well mixed precursors, there is no mixing time to reduce, there is no mixing time to reduce the time resolution of the technique, and also since the beam is generally falling on the sample reaction mixture at the middle. So, possibility of reactions on the vessel wall, okay, is minimized. Okay. So, I will talk on this flash photolysis, laser flash photolysis nowadays term is, laser flash photolysis is the nowadays term. Okay. Previously I mean discharge lamps are used as the source of flash. Nowadays lasers are used. Okay, so I will talk in a more detail about this flash photolysis and what is laser in a later part of I mean in another class. There is another technique, like another variation of flash photolysis, which is also used for studying the fast reactions. This is called your pulsed radiolysis. It is a variation of flash photolysis in which a short pulse of high energy electrons, 10 to the power minus 9 to 10 to the power minus 6 second, duration is that much, is passed through the sample in order to initiate the reaction. For very fast processes, the pump probe technique is often used, in which pulsed lasers are employed both to initiate the reaction and also to detect the products by pulsed spectroscopic technique. The time separation between two pulses can be varied, maybe electronically or maybe by using the optical delay line. Okay. So, in one case you pump with a laser, generating your excited state species or maybe reactive species, like you have got your energy level diagram over here. Say this is your substance which is the reactant, maybe not in the ground state but in the excited state. So, here say you pump, like you pump water from from the lower level to the upper level, maybe in a housing complex, and then it is stored into your water tank. This is your pump. Then suppose this excited species undergo some chemical reaction producing another species, and say this species has got some absorption in another region. So, another say this is your species. So, another probe laser is used to probe this one. So, this higher state absorption. Okay. So, when you shine with another probe light, so what it is doing is that this probe light is absorbed by this species. So, reduction in probe light intensity has been used to monitor the extent of reaction, or how much this reactive species is generated, or maybe time development of this species, that is with time how the concentration of this species, this reactive species or the product is changing with time. So, that is our goal. I mean, to study kinetics, you need to find out, you need to know the concentration of certain substance, maybe it is reactant or maybe it is product, how it is changing with time. So, if you know this time, if you know the concentration as a function of time of that particular species, you will be able to know the kinetics, okay, the rate of reaction rate constants. There is another method which is called the relaxation method. So, for studying fast reactions, if we allow a chemical system to come to equilibrium and then perturb the equilibrium in some way, maybe suddenly you do something, maybe you do a rapid temperature change, maybe rapidly you push the system external, that is you put pressure, or maybe you change the volume very fast. Okay. So, in some way you change the equilibrium. Okay. The rate of relaxation to a new equilibrium position provides information about the forward and reverse rate constants for the reaction, and since a system at chemical equilibrium is already well mixed, the relaxation methods overcome the mixing problem associated with any flow methods. Okay. So, the system is in equilibrium initially. Okay. So, this is your equilibrium system, and then what you do, you perturb. So, system is now perturbed. So, it will try to find out another equilibrium state in this perturbed condition. Okay. So it will tend to relax to a new equilibrium system. So you want to follow that. You would like to follow that. Okay. So it does not suffer from the problems of mixing associated with the relaxation methods. I mean associated with the flow methods. Okay. So mixing problem is overcome in this relaxation method. Okay, because flow methods have real problem of mixing. So mathematically we can have this one, that we want to find out the time constant of a reaction changing from one equilibrium state to another. Okay, so A to B equilibrium, at equilibrium state 1 you can write this rate of change of concentration with time, you can write this one, and this is correspondingly you can write this. A sudden change, as for example temperature, is introduced at time t equal to 0. So the success of this method is that you have to change, or you have to perturb very fast. If your perturbation takes time, then it is not very useful. So it relies on the fact that how fast you can perturb. So the moment it is perturbed, then it will try to relax, the system will try to relax from the one equilibrium state to another equilibrium state with time, and that will guide you to find out the kinetics of the process. So after sudden change you get new equilibrium. This is equilibrium 1, this is equilibrium 2. So this is equilibrium 1 corresponding expression, this is equilibrium 2 expression. Okay. The overall change of concentration of A between equilibrium 1 and equilibrium 2 due to it takes time, this much of time t. If it is x0, so x0 is equal to this much. Okay. The rate of change of A during t equal to, so you can write this one, t equal to 0 to t, and integration, and then taking this that t is equal to 1 by this, we have this one where tau is the time for relaxation, this is your relaxation time. So from this, from these calculations and this mathematical manipulation and writing your equilibrium constants, new equilibrium constant like this, you can find out kf forward and kr, forward rate for the second equilibrium case, and the backward rate for the for your second equilibrium can be determined. So this method relies on how fast you can perturb. Okay. So this is another useful method, that is the relaxation method, like other methods I talked about. This is also a very useful method, but it relies on the fact that how fast you can perturb your system. If you perturb your system very slowly, then the system will also try to relax slowly, and so maybe in that case it will not be very useful to follow your fast kinetics. Okay. So fastness, to follow fastness, fast process, you have to perturb very fast. Okay. So we talked about flow methods. Okay. So AB mixing chamber, then it is flowing out. So you are you are moving your detector from here to here, since you know the flow rate. So time difference, how much time should the reactant, mixed reactant take while moving from this position to this position, will give you the time difference. So from that you can find out the rate. That is, different location of a detector reflects different time. Stopped flow, these two are mixed very fast, and then this one stops the flow. Okay. And the moment it is stopped, flow is stopped, you keep on injecting, so it is coming out this cylinder is coming out. Okay. So, that means what is happening, that you can find out, you can find out the concentration, I mean in terms of absorbance or maybe fluorescence of, I mean concentration of your reactant or maybe your product, you can find out. And I also talked about this flash photolysis, and there are still many methods. Okay. Now, next thing is determination of concentration of reactants. Most kinetic measurement involve monitoring the concentration of reactants at different times. As I told you that for slow reactions, so maybe you monitor concentration at say I mean 2 minutes interval, or maybe 5 minutes interval, or maybe 10 minutes interval, okay, and then by simple titration. In some kinetic studies, the conversions of reactants at constant time is measured. Okay. Say after 2 minutes how much reactants are converted, you measure. That is, or that can also be a technique. Many analytical techniques can be employed to detect concentration. One is volumetric measurement, as I told you that simple titrations are used to find out the concentration, maybe acid base titration, maybe precipitation titration, maybe conductometric titration, maybe there are several ways, maybe pH metry. With time you find out the pH, how pH is changing with time. That can also be a good way of looking into the concentration. Okay. So, this is the volumetric measurement. Another thing, I mean other things are instrumental measurements like spectrophotometry using Lambert-Beer's law. You can find out the concentration. That is, I told you that using a suitable method you find out, in the during our first part of the lecture today, I talked about by any suitable method. I told you that the composition of reaction mixture is monitored at one or more positions along the tube by any suitable method. So, that I mean suitable method means your maybe spectrophotometry, maybe spectroscopic method, mass spectroscopy, IR spectroscopy, X-ray photoelectron spectroscopy, XRD, X-ray diffractometry, NMR, etc., nuclear magnetic resonance. It may be chromatography, gas chromatography, liquid high performance liquid chromatography, high pressure, then FPLC, fast protein liquid chromatography, and so on. Okay. pH, conductivity, as I told you, maybe temperature, maybe pressure, maybe volume, okay, and specialized techniques as I just talked about can be useful in finding out, in determining the concentration of reactants. Okay. So, these are instrumental methods. Okay. These are all instrumental methods. By using instrumental techniques, you will be able to find out the concentration. In case of spectrometry, it relies on the fact that out of your many reactants, or maybe I mean suppose there are 2 reactants and say there are 2 products, maybe out of these 4 species, maybe one out of these 4 is absorbing at a fixed wavelength, maybe say at 500 nanometer. So, what you do, you monitor absorbance at 500 nanometer as a function of time. Okay. That will give you the concentration. Okay. And even if your detector is very fast detector, then you can follow their concentration using absorbance spectroscopy also, maybe also by fluorescence. With time you monitor the fluorescence. If it is a very short period of time, maybe say 1 nanosecond, maybe 1 picosecond, even in that case you can find out the signal. So, from the intensity of your signal or from the height of your signal as a function of your of time, you can find out you can find out the rate constant of the decay, or maybe rate constant of the rise of the signal, either way. There is another method which is called the shock tubes. The shock tube method provides a very way of producing highly reactive atomic or molecular radical species through rapid dissociation of molecular precursor without the use of a discharge or laser pulse. In that case, you don't use any laser pulse, maybe discharge or maybe discharge. You don't use anything. So, what you do, you just put some shock. The method is based on the fact that a very rapid increase in pressure, that is the shock, causes a rapid heating of a gas mixture. Generally, gaseous reactions are followed through shock tube method, and rapid heating of a gas mixture to a temperature of several thousand Kelvin. So, a huge increase in temperature, and in many dissociation reactions it has been found that these reactions are endothermic. So, at high temperature their equilibrium is shifted towards the products. A rapid increase in temperature therefore leads to a rapid production of reactive species, that is dissociation of products, initiating the reaction of your interest. A shock tube essentially consists of two chambers separated by a diaphragm. One chamber contains the appropriate mixture of reactant and precursor, and the shock wave propagates through the reaction mixture. The temperature rise can be controlled by varying the pressure and composition of the inert gas, and composition of the reaction mixture after initiation is monitored in real time using spectroscopy. So, this is a spectroscopic detector. So, inert driver gas at high pressure, it is your reaction mixture, and there is a diaphragm. Okay. So, to initiate the reaction, the diaphragm is punctured and a shock wave is propagating through the reaction mixture. So, you have to puncture it. It is a very high pressure. Okay. So, if you puncture, then it rapidly flows. I mean, this high pressure, under high pressure this gas was there. Okay. So, rapidly it flows from here to here, causing a huge increase in temperature. That is a shock. Okay. So, the shock tube approach is often used to study combustion reaction, and suitable precursors for such studies together with radical species obtained on dissociation using argon as shock gas include. So, these are the typical example of shock, example of reaction studied by shock method, shock tube method. Okay. So, you have got your high pressure inert gas. So, it is not going to hamper your reaction, hamper in the sense that it is not going to react with your reaction mixture. So, it is a means to provide your shock. Okay. So, it is a huge pressure. So, the moment this is released through by making a puncture, so it will pass through, and it is temperature is increased several thousand Kelvin, rapid heating. Okay. So, rapid heating causes the reaction to be initiated, and then reaction is followed by the help of a detector. Okay, these are the examples. Now, the shock method does have some major difficulties. The fact that the rapid heating is not selective for a particular molecule and is likely, suppose you have got more than one molecules in the mixture and you want to selectively heat one molecule, it is not possible. Okay, that is why rapid heating is not selective for a particular molecule and is likely to lead to at least partial dissociation of all the species in the reactant chamber. This leads to a complicated mixture of reactive species and often large number of reactions occurring in addition to reaction under study, in addition to the reaction which is of our interest. Okay. So, modeling the kinetics of such reaction is very challenging, and the problem is that sometimes it is difficult, difficult to reproduce the reaction. Suppose you do some reaction using in a shock tube by puncturing your high pressure argon or helium gas. The second time you want to do, maybe since it is a mechanical way of puncturing, you may not be able to reproduce the first one. So, that is why it is a very challenging one, and modeling is sometimes very difficult, because you cannot selectively hit, out of many a particular molecule. Okay. So, let us look into various techniques. Although we are interested now, we are focusing onto the fast reactions, but anyway. So, let us have a look into various methods. Conventional method: mix reactants together in a batch reactor, measure concentration versus time. So, it is I mean time required is 10 seconds or more. It may take more time, 10 seconds or more. For stopped flow, set of continuous flow systems where reactants are fed into the reactor and flown out again quickly, that there is negligible reaction. Stop the flow so that the reaction can react, I mean reactants can react, and measure the conversion versus time. So, in that case it is 10 to the power minus 1 second or more. Okay. Temperature jump method. Temperature jump method is the mix reactant at such a low temperature that the reaction rate is negligible. Okay. Use carbon dioxide laser to suddenly heat the reactants and measure concentration versus time. Okay. So, in that case you get 10 to the power minus 6 second, I mean in that case your time required is 10 to the power minus 6 second or more. Okay. That is the limit, 10 to the minus 6. Shock tube, it takes about 10 to the minus 3 to 10 to the minus 5 second, and in that case put 10 to the minus 1 atmospheric pressure of one reactant and 10 atmospheric helium on the other side of the diaphragm. Okay. And put maybe 10 to the minus 3 atmospheric pressure to other reactant on the other side of the diaphragm. Suddenly break the diaphragm so that the gas flows from high pressure side to the low pressure side. Okay. A huge heating, and measure the reactant concentration versus time. Flash photolysis, okay. It is from 10 to the minus 9 nanosecond to 10 to the minus 1 second subsecond. So, put reactant into vessel under conditions where reaction is negligible. Okay. Say it is a say consider a reaction which does not generally occur in the ground state, maybe in the excited state. I mean when out of two reactants, maybe one is excited and then it does the reaction. In that case flash photolysis is useful maybe. So, a pulse laser, in that case a pulsed laser or flash lamp is used to initiate the reaction, okay, and measure the reactant concentration or maybe the product concentration as well. In all the cases, as I told you, that measure reactant concentration, maybe you can measure reactant concentration or maybe product concentration depending on your choice, or maybe depending on the fact that which one is easier to do, whether it is easy or whether it is not easy. NMR, initiate the change with a magnetic pulse and measure the decay of spins with NMR. Okay, that will give you the idea. I mean 10 to the minus 2 10 to 10 to the minus 2 seconds to 10 to the minus 9 seconds. Okay. So, and the conventional flow system continuously fed reactants into a reactor and measure the steady state reaction rate, and it's the time constants are 10 to the power minus 3 seconds or more. Molecular beam, direct beams of reactants towards each other, I mean like that. Say we have got a beam of molecules, say one is doing this way, another is going this way. So, there is the interaction at this point. Okay. So, reaction is happening at this point. So, and you can study how much of reaction is taking place, maybe by using a suitable detector over here. Okay. Again here the time constants are like 10 to the power minus 13 to 10 to the power minus 13 to 10 to the power minus 9 second. Okay. So I mean we have now seen the time constants and various also the various basics of various techniques to follow mainly the fast reactions. Okay. So it looks like that in some cases this flow techniques are not useful because of the slowness, because of the fastness of the process. In some cases maybe flash photolysis could be useful, not always flash photolysis is useful. If excited state reaction is taking place, maybe say excited state intramolecular proton transfer, maybe excited state hydrogen atom transfer, in that case these light induced detection processes or light induced processes like flash photolysis are very useful. Okay. So let us again come back to what we have learned today. So we started with importance of chemical kinetics in our life, and why do we need to study chemical kinetics? Because we want to know the how some reactants are depleted, maybe how we are growing in height. Okay. So there must be definitive chemical process that is happening. The process is going on with time. Okay. So it must have some kinetics. Now in case of conventional processes for studying reactions where the reaction is not very fast, you can use conventional techniques like say titration, but for studying fast reactions you have to adapt a method, adapt ways by which you can compete with the fastness of the process. Okay. Like whenever you want to catch a train which has just started to move, what you have to do, you have to run. Okay. And the moment your speed is close to the speed of the train, then you can get into it, otherwise it is difficult. So like that your method should compete with the speed of the reaction. If your method is very slow, then during your measurement you may miss many things, the details of the process may be missed. But if you can follow, if you can detect very fast, then maybe details of the processes can be achieved. Okay. So one method was like I talked about is the flow technique, then it is the modified version is the stopped flow technique. Then he talked about given just idea about this flash photolysis. Another version was the pulsed radiolysis. Relaxation method is also a very important thing, that is it relies on the fact that you have to part of the system, that is an equilibrium system, such that a new equilibrium is established. So during establishment of new equilibrium you can follow how fast or how slow it is equilibrated to a new description. Okay. And we have compared, and another method was a shock method, preferably for gaseous reaction it is used, and we have compared various methods and their time constraints. Okay. So in the next lecture we will talk about this in a little detail of the technique which is called the flash photolysis and also the laser flash photolysis, and there we will have chance to know a little about flash photolysis, I mean little about flash photolysis, laser flash photolysis, and what is laser, okay, and what is the difference between a laser and a laser light or laser source with the simple light. So that will we will try to cover in the next lecture. So till then, have nice time. Thank you.